Hey everybody, and welcome back to Algebra 2 Online. I want to talk today about systems of three equations. So in three equations, we're talking about like x, y, and z, and we're going to be basically thinking about when do planes intersect. And there's actually three solution options here, and then there's three cases where you're going to get no solution. And we're not really going to do like systems of four equations or five or anything like that, but the idea is honestly the same. You're still looking for where do all three things or all four things or five things or whatever you have intersect. And it just gets more and more complicated to basically visualize. So we don't really usually go higher dimensions, but in three dimensions, we can definitely visualize it. So the solution cases are basically these three. And the first one is basically the idea that like all the planes are sort of oriented, almost like they were like rotated, I think, around a common line of intersection. And then that line actually becomes the solution. So this is the case where we're going to get infinite amount of solutions. Again, it's not like all real numbers. It is not all real numbers because, you know, there's points like over here in the yellow plane, for example, that have that are not part of that line, so not part of the solution. This one's just hard to draw. So the idea on this one is kind of like when the two lines are maybe overlapping. Here it's like you've got three planes that overlap. And if they're just exactly the same plane, then you're going to get, again, infinite solution. Any point in the plane would be a solution. And then this is kind of your standard, I guess, case. This is just one solution, and it's trying to show you like all of the planes are tilted just so you're getting like one point of intersection right there. So those are the good cases. The bad cases are basically drawn down here. So these ones are your no solution cases. Whoops, that was bad no solution symbol. OCD must redo. Oh man, bad again. Okay. But you can see in these cases you don't have all three intersecting. Like you could have two intersect right there or right there, right there, but you don't have all three, so that's no solution. You could have again two, but not all three, and you could definitely just have three parallel planes, which would mean, again, no solution. So today I just really want to take time to show you how to do these algebraically, because I would never ask you to graph planes like this and just visualize when they intersect or not. It's just a really, really tough question to ask someone to do that. So we really just do them algebraically. It's another reason why I really don't like graphically solving systems of two equations, because it's not useful. So why learn it? This one, when I first look at systems of three equations, I am trying to figure out, do I want to do it algebraically with elimination or substitution? And if I look, I can see along the kind of leftmost column, in a sense here, I have a common multiple, 2, 4, 6, right? And nowhere in here do I have a variable that's easy to solve for. So it makes sense to do elimination. And if you had read this, you would have seen that that's kind of where we're going. The idea with elimination in three equations is basically to just eliminate the same variable using two different pairs. So you could eliminate, I'm going to eliminate x because those are like the common multiple. But I could eliminate x using this pair and this pair, or the first and the third. So basically you only have 3 pairs to choose from: 1, 2, 1, 3, or 2, 3. And I'll try to keep this organized and color-coded. So I'm going to take pair 1, and I'm going to multiply by 2, right? And I would get negative 4x plus 10y plus 6z equals negative 50. And then I would have, I'm just going to copy that. And then this is a case where you want to subtract these, right? And if you subtract, then you can eliminate the x's. So 10 minus a negative 3y would be 13y's. 6 minus a negative 8z would be adding them. You get 14. And negative 50 plus 39, right? Because double negative would give you negative 11 here. So I'm going to kind of just circle this for right now. So that would be eliminating x in the first pair. And then maybe I will do, so I'm going to do this and this now. So I'm going to use basically equation 1 and 3, and I'm going to multiply equation 1 by 2, and then, 3, and then it will match up the 6x and the 6x, and I can eliminate x that way. So I'm going to do this down here. So I got negative 6x plus 15y plus 9z equals negative 75. And then I'm just going to copy that third equation down. And then in this case, if I add them, right, I can eliminate the x's, right? So 15 plus 8 is 23. And then 9 minus 5 is 4z. And negative 75 plus 14 is negative 61. So that is all that work just to do this first thing. So I used elimination techniques, and I eliminated the same variable using 2 different pairs of equations. And I used pair like equation 1 and 2, and then I used 1 and 3. Just make that part easy on yourself. Don't try to eliminate z or something here, because 3 and 8 and 8 and 5, they're going to be like annoying to deal with. You're going to have to multiply both equations by something to eliminate. So now I need to, those 2 equations I circled, basically the whole problem just restarts now. It's like I have a system of 2 equations, a y and a z system, and I just need to solve that using whatever techniques I basically want. So why don't I copy this down here? And if I was solving this system, I would not do substitution because it's not super easy to solve for a variable. And so basically I would do elimination, and it's kind of annoying, but I would probably just eliminate z, I guess. It's not like one of them is particularly easier here. So I would just multiply the first by 4 and the second by 14, so then the z's should be able to be eliminated. So the first equation would become 52y plus 56z minus 154. And the second equation would become 322y, 56z, and negative 854. And then if you go and subtract these, right? You'll kill off all the z's. Wait a second. I just noticed. This makes no sense. I just somehow 2 seconds ago said negative 11 times 4 is negative 154. I don't know what I just did. So let me restart that. Sorry about that. Okay. So that's 52. That is 56, definitely. That is negative 44. And then this is definitely 322. This is 56. And this is negative 854. So then when we subtract these, we would get negative 270y equals 810. And that would mean that y equals negative 3. That's a nice number, which is good. Not necessarily needs to be a nice number, but I made this problem nice. So, systems of two equations, right? We take this, and we're going to go take that, and we're going to plug it into either of these two equations to get the other variable. And I would always pick the easy equation, so this would definitely be the easy one, because the numbers are just smaller. So if I go plug in, we got 13 times negative 3, and then plus 14z equals negative 11. So I'm going to take this, put it right in here, and I would get, I'm just going to solve it out quickly. Z would be 2 if you solve that out. So that is another nice number, which is nice here. So basically, all that was just solving a system of two equations, and then we just use the two variables that we've solved for, and we are going to solve for the final third one. So the idea is, just like before with systems of two, we used 1 to get the second one. Now we're going to use 2 to get the third one. And basically, you can go back to any of these equations and just plug in the 2 you have and solve for the third one. So I would pick that one because it's the quickest and easiest one. So we have 2x plus 5 times negative 3, which is y, right? Plus 3 times 2 needs to equal negative 25. And then that would mean 2x equals negative 16. So x would be negative 8. And I could go through the check, but these three, they do have to work for all three of these equations, make all three true, and you can definitely just go and plug in x, y, and z, and you would see that it actually does work. If you go plug all these in, they really solve this equation, and this one. So these three are really your answer. That's the point that works for all three planes. It's basically one of these cases right here. So I want to go through an example for substitution now. And the reason this one would be substitution is because you have a variable that's really easy to solve for. So I would solve for that y and get y equals negative 36 plus 5z plus 4x. And then you can take this and you can plug it into these two right here. So we just did that. And then we're going to sub that y value into the first and the third equation. And if we do that, we should basically get a system of two equations, and then it works just like the last problem. You solve the system of two equations, and then you back solve from there to get the third and final variable. So I'm going to sub into the first one first. So we have 3x minus 2 times negative 3x plus 5z plus, nope, not 9, that's a 4. I just don't know how to write 4s, I guess. 4z. And that's just y, so I plugged it in for y. And then plus 4z equals 35. And then I'm going to simplify this equation. So we have positive 72, we have negative 10z, we have negative 8z. No, we don't. There's not two z's. This should be an x, and so this should be an x now. Okay. And plus 4z equals 35. And then, let's see, negative 5x, we're going to get negative 6z, and I'm going to move this 72 over to the right. If we do that, we get negative 37. And I would basically hold off doing any more right now. There's no more like simplifying to do or anything. So this was y into equation 1 right here. Now I'm going to do y into equation 3 right here. Okay, and if I go ahead and simplify that, I would get the following. And then just combining like terms, so I see we have 5x minus 12, so it's going to be negative 7x. We have minus 15, positive 3, so that's negative 12z. And then I'm also going to move this 108 just over to the right. If we do that, we would get negative 77. So now I took my 3 variables and I boiled it down to a system of 2 equations, right? So I've kind of got equation like A, let's say, and equation B, and the whole process just restarts now. And I'm just trying to solve for x and z, and I think, do I want to do substitution? Do I want to do elimination? And I can see that I have this 6z and this 12z, so elimination would probably be good with z. So I'm going to do 2 times a, basically, and if I do that, I would get negative 10, yes, negative 10x minus 12z equals negative 72, and then I'm just going to copy that other equation, like b, down here, and then if I find a color I like, how about purple? If I subtract these, right, I could eliminate z. And then I would have negative 3x equals, okay, so, yeah, this should not be here. This should be 74. There we go. Okay. I was beginning to worry about my numbers there. So now if I do negative 74 plus 77, you get 3. Whoops, I want to keep my colors the same. It's probably good to show you that even after doing many of these problems in my life, you still can make tons of mistakes with these. It's very easy to do that. So that is x, finally. And then you can go back to any equation that just has x and z. So really you got like three, I guess. You got this one, and this one. But I would pick the easiest one. So I would pick this one. And if I go plug in -1 for that, so we got, maybe we'll just keep with purple for right now, -5. And then I'm going to plug in my -1 in there in a second here. So my -1 goes in there. And then in this case, I'd get -6z equals -42 if you like multiply these two, and then you'll be subtracting them over. So then if you just divide by -6, you get that z is 7. And then now you just want to go back to the beginning, and you want to pick an equation, maybe this one, that would be a good one to solve to get the third and final variable, which is y, right? So I will just do very, like running out of room here, but if I plug in 7 for z and -1 for y, right? So I'm just plugging in here. I'm plugging in 7 and -1, and you could really just go to a calculator, which I'm going to do right now, because I am not trusting my mental math today. You should get -5. So that, I'm going to put that in the middle here. So they're all kind of lined up. So these three would be the answer. Basically, these three planes intersect at a point -1, -5, 7. That would be your final answer. So just to kind of recap, substitution, solve for a variable, plug it into the other two equations, simplify them as much as possible, like I did here. Then you get a system of two equations, and you can solve that using whatever technique you want. Then basically you're going to just take your two, in this case it was x and z, your two first variables that you solved for, and you get your third and final, which in this case was y. For elimination, you pick a pair. You pick two different pairs. So I picked pairs equations 1 and 2, and then 1 and 3, and I set it up with multiplication so that I could eliminate the same variable in both equations. You got to do the same variable. Then you get two equations, two unknowns. Solve those any way you want, and then again back solve. So this was me using y and z. I could get x last, and I always recommend you pick the easiest equation when you do that last part. So that was the easiest equation right there. And all we're doing is we're basically figuring out, do the three planes now. That would be the analog in 3D. Do the three planes, like the analog to a line. So do the three planes intersect? And if so, where do they intersect? What point of intersection is it?